Electricity. All of us agree the importance of electricity in our daily lives. But what is electricity? Electric charge and electrical forces. Electrons have a negative electrical charge. Protons have a positive electrical charge. These charges interact to create an electrical force. Like charges produce repulsive forces so they repel each other, e.g. electron and electron or proton and proton repel each other. Unlike charges produce attractive forces so they attract each other, e.g. electron and proton attract each other. Electrostatic charge. Electrons move from atom to atom to create ions. Positively charged ions result from the loss of electrons and are called cations. Negatively charged ions result from the gain of electrons and are called anions. The charge on an ion is called an electrostatic charge. An object becomes electrostatically charged by friction, which transfers electrons between two objects in contact with a charged body, which results in the transfer of electrons. Induction, which produces a charge redistribution of electrons in a material. Charging by induction. Electrical conductors and insulators. Electrical conductors are materials that allows free movement of electrons inside metals are good conductors of electricity. Silver is the best electrical conductor. Electrical non-conductors, insulators, are materials that do not allow movement of electrons easily. Examples are wood, rubber, etc. Semiconductors are materials whose conductivity lies in between those of conductors and insulators. Examples are silicon, arsenic, germanium. Measuring electrical charges. The fundamental charge is the electrical charge on an electron and it has a magnitude of 1.60 to 189 to x 10 to 19 c. The electrical charge, Q, is a discrete quantity and it is always measured as Q equals NE, where E is the fundamental charge. Conservation of charge is a fundamental principle which states that charge can neither be created or destroyed but can only move from one atom to another. Coulomb's law. Electrical force is directly proportional to the product of the electrical charges and inversely proportional to the square of the distance. Force fields. The configuration of space around an object is changed by the presence of an electrical charge. The electrical charge produces a force field, called as electrical field. A map of the electrical field can be created by bringing a positive test charge into an electrical field. When brought near a negative charge, the test charge is attracted to the unlike charge, and when brought near a positive charge, the test charge is repelled. You can draw vector arrows to indicate the direction of the electrical field. This is represented by drawing lines of force or electrical field lines. These lines are closer together when the field is stronger and farther apart when it is weaker. A positive test charge is used by convention to identify the properties of an electric field. The vector arrow points in the direction of the force that the test charge would experience. Electric lines of force diagram for A, a negative charge, and B, a positive charge when the charges have the same magnitude as the test charge. Electrical potential. An electrical charge has an electrical field that surrounds it. In order to move a second charge through this field, work must be done. Bringing a like-charged particle into this field will require work since like charges repel each other, and bringing an opposite-charged particle into the field will require work to keep the charges separated. In both of these cases, the electrical potential is changed. The potential difference, P, that is created by doing 1.00 joule of work and moving 1.00 coulomb of charge, is defined as 1.00 volt. A volt is a measure of the potential difference between 2 points. Electric potential equals work done / charge, or P equals W / Q. The voltage of an electrical charge is the energy transfer per coulomb. The energy transfer can be measured by the work that is done to move the charge or by the work that the charge can do because of the position of the field. Electric current. Electric current means the flow of charges, which is analogous to water flow. It is the charge that flows, and the current is defined as the flow of the charge. An electrical circuit contains some device that acts as a source of energy as it gives charges a higher potential against an electrical field. The charges do work as they flow through the circuit to a lower potential. The charges flow through connecting wires to make a continuous path. A switch is a means of interrupting or completing the circuit. The source of the electrical potential is the voltage source. A simple electric circuit has a voltage source, such as a generator or battery, that maintains the electrical potential, some device, such as a lamp or motor, where work is done by the potential, and continuous pathways for the current to flow. Voltage is a measure of the potential difference between two places in a circuit. Voltage is measured in joules/coulomb. The rate at which an electrical current, I, flows is the charge, Q, that moves through a cross-section of a conductor in a given unit of time, t, I equals Q/t. The units of current are coulomb/second. A coulomb/second is an ampere, up. What is the nature of the electric current carried by these conducting lines? It is an electric field that moves at near the speed of light. The field causes a net motion of electrons that constitutes a flow of charge, a current. Electrical resistance. Electrical resistance is the resistance to movement of electrons being accelerated with an energy loss. Materials have the property of reducing a current, and that is electrical resistance, R. Resistance is a ratio between the potential difference, E, between 2 points and the resulting current, I. R equals V/I. The ratio of volt/amp is called an Ohm. The relationship between voltage, current, and resistances, V equals IR. This is known as Ohm's law. The magnitude of the electrical resistance of a conductor depends on 4 variables: the length of the conductor, the cross-sectional area of the conductor, the material the conductor is made of, the temperature of the conductor. Resistors can be connected in series, that is, the current flows through them one after another. The circuit here shows 3 resistors connected in series, and the direction of current is indicated by the arrow. Note that since there is only one path for the current to travel, the current through each of the resistors is the same. I1 equals I2 equals I3. Also, the voltage drops across the resistors must add up to the total voltage supplied by the battery. V total equals V1 plus V2 plus V3. R equivalent equals R1 plus R2 plus R3. Resistors can be connected such that they branch out from a single point, known as a node, and join up again somewhere else in the circuit. This is known as a parallel connection. Each of the 3 resistors in the figure below is another path for current to travel between points and me. Head of the potential must be the same for each resistor. Similarly, head B the potential must also be the same for each resistor. So, between points and me, the potential difference is the same. That is, each of the 3 resistors in the parallel circuit must have the same voltage. V1 equals V2 equals V3. Also, the current splits as it travels from A to B, so the sum of the currents through the 3 branches is the same as the current at A and at B, where the currents from the branch unite. I equals I1 plus I2 plus I3. Electrical power and electrical work. All electrical circuits have 3 parts in common: a voltage source, an electrical device conducting wires. The work done, W, by a voltage source is equal to the work done by the electrical field in an electrical device. Work equals power x time. The electrical potential is measured in joules/coulomb and the quantity of charge is measured in coulombs, so the electrical work is measured in joules. A joule/second is a unit of power called the watt. Power equals current x potential, or P equals IV. Magnetism. All of us are familiar with magnets. In a magnet we have magnetic poles, the north and the south pole. A north-seeking pole is called the north pole. A south-seeking pole is called the south pole. Like magnetic poles repel and unlike magnetic poles attract. Magnetic fields. A magnet that is moved in space near a second magnet experiences a magnetic field. A magnetic field can be represented by field lines. The strength of the magnetic field is greater where the lines are closer together and weaker where they are farther apart. The source of magnetic fields, permanent magnets, moving electrons produce magnetic fields. In most materials these magnetic fields cancel one another and neutralize the overall magnetic effect. In other materials such as iron, cobalt, and nickel, the atoms behave as tiny magnets because of certain orientations of the electrons inside the atom. These atoms are grouped in a tiny region called the magnetic domain. Our Earth is a big magnet. The Earth's magnetic field is thought to originate with moving charges. The core is probably composed of iron and nickel, which flows as the Earth rotates, creating electrical currents that result in the Earth's magnetic field. The Earth's magnetic field. Note that the magnetic North Pole and the geographic North Pole are not in the same place. Note also that the magnetic North Pole acts as if the South Pole of a huge bar magnet were inside the Earth. You know that it must be a magnetic South Pole since the north end of a magnetic compass is attracted to it and opposite poles attract. A bar magnet cut into halves always makes two complete magnets with both a north and a south pole. The poles always come in pairs. You cannot separate a pair into single poles. Electric currents and magnetism. First had discovered that a compass needle below a wire pointed north when there was not a current. B moved at right angles when a current flowed one way, and C moved at right angles in the opposite direction when the current was reversed. A. In a piece of iron, the magnetic domains had random arrangement that cancels any overall magnetic effect, not magnetic. B. When an external magnetic field is applied to the iron, the magnetic domains are realigned, and those parallel to the field coincide at the expense of the other domains, and the iron becomes magnetized. Applications of electromagnets, electric meters. The strength of the magnetic field produced by an electromagnet is proportional to the electric current in the electromagnet. A galvanometer measures electrical current by measuring the magnetic field. A galvanometer can measure current, potential difference, and resistance. A galvanometer measures the direction and relative strength of an electric current from the magnetic field it produces. A coil of wire wrapped around an iron core becomes an electromagnet that rotates in the field of a permanent magnet. The rotation moves water on a scale. Electric motors. An electrical motor is an electromagnetic device that converts electrical energy into mechanical energy. A motor has two working parts: a stationary magnet called a field magnet and a cylindrical, movable electromagnet called an armature. The armature is on an axle and rotates in the magnetic field of the field magnet. The axle is used to do work. Electromagnetic induction. Induced current. If a loop of wire is moved in a magnetic field, the voltage is induced in the wire. The voltage is called an induced voltage and the resulting current is called an induced current. The induction is called electromagnetic induction. A current is induced in a coil of wire moved through a magnetic field. The direction of the current depends on the direction of motion. The magnitude of the induced voltage is proportional to the number of wire loops cutting across the magnetic field lines, the strength of the magnetic field, the rate at which magnetic field lines are cut by the wire. Applications: DC and AC generators, transformers, step up and step down. Heating effects. Energy exists in various forms such as mechanical energy, heat energy, chemical energy, electrical energy, light energy and nuclear energy. According to the law of conservation of energy, energy can be transformed from one form to another. Joule's laws are a pair of laws concerning the heat produced by a current and the energy dependence of an ideal gas to that of pressure, volume, and temperature, respectively. They are named after James Prescott Joule. Joule's first law, also known as the Joule effect, is a physical law expressing the relationship between the heat generated by the current flowing through a conductor. Joule studied this phenomenon in the 1840s. It is expressed as Q equals I to asterisk R asterisk T, where Q is the heat generated by a constant current I flowing through a conductor of electrical resistance R, for a time T when current, resistance and time are expressed in amperes, ohms, and seconds respectively. The unit of Q is the Joule. Joule's first law is sometimes called the Joule-Lenz law since it was later independently discovered by Heinrich Lenz. The heating effect of conductors carrying currents is known as Joule heating. Chemical effects. Electronics depend on chemistry more than you can imagine. In order to generate electricity there are many methods used, one of them is chemical. Remember batteries, where electricity is generated because of chemical reactions inside cell. Also in conductors like liquids and gases electricity is carried not by electrons as it is in solid constructions left parenthesis copper, aluminum, etc., but by ions molecules with electric charges. Even non-distilled water contains enough ions to be conductive. Let's go through several chemical effects of electricity. In chemistry and manufacturing, electrolysis is a method of using a direct electric current, DC, to drive an otherwise non-spontaneous chemical reaction. Electrolysis is commercially highly important as a stage in the separation of elements from naturally occurring sources such as ores using an electrolytic cell. Faraday's single quote S law of electrolysis is stated below. Faraday's first law of electrolysis: the mass of a substance altered at an electrode during electrolysis is directly proportional to the quantity of electricity transferred at that electrode. Quantity of electricity refers to the quantity of electrical charge, typically measured in coulomb. Faraday's second law of electrolysis: for a given quantity of electricity, electric charge, the mass of an elemental material altered at an electrode is directly proportional to the element's equivalent weight. The equivalent weight of a substance is its molar mass divided by an integer that depends on the reaction undergone by the material. Electroplaning is a planing process in which metal ions in a solution are moved by an electric field to cold an electrode. The process uses electrical current to reduce cations of a desired material from a solution and coat a conductive object with a thin layer of the material, such as a metal. Electroplaning is primarily used for depositing a layer of material to bestow a desired property, e.g., abrasion and wear resistance, corrosion protection, lubricity, aesthetic qualities, etc., to a surface that otherwise lacks that property. Another application uses electroplaning to build up thickness on undersized parts. The process used in electroplaning is called electrodeposition. End of the topic.